This is Dr. Anthony Revis, and this is SVSU, General Chemistry 111, Chapter 7, Lecture 2. That's Lecture 2 of Chapter 7, Chemical Bonding and Molecular Geometry. In this chapter, we will cover ionic bonding, covalent bonding, Lewis symbols and structures, formal charges and resonance, strength of ionic and covalent bonds, and molecular structure and polarity. These topics will be covered, but not necessarily in this order. Electrical dipole moment is the measure of the electrical polarity of a system. In our case, the system is a molecule or a compound. So in other words, the electrical dipole moment or electrical dipole or dipole moment measures the electrical polarity of the system. It allows us to get an idea of which area of the molecule or compound the polarity has shifted to. And when we think of polarity shifting, we think of electrons shifting to that area. So essentially it allows us to understand which area of the compound or molecule has a higher proportion of negative charges and which area has a lower proportion of negative charges. The molecular dipole moment measures polarity in a molecule or covalent compound. If a molecule has a molecular dipole moment, then it is considered polar. So polar molecules are detected by their dipole moment. A polar molecule contains a positive pole and a negative pole. One end of the molecule has a partial positive charge for the positive pole. The other end of the molecule has a partial negative charge for the negative pole. Now, it's important to recognize that there are no positive or negative poles in a nonpolar molecule. In a nonpolar molecule, the electrons are equally distributed throughout the molecular structure. So let's talk then about that molecular polarity and polar bonds within molecules, within compounds, within structures. A polar covalent bond, or polar bond, is a covalent bond with a greater electron density around one of the two atoms in the molecule. So in other words, there will be a shift towards one atom in the molecule compound over the other. We take, for example, hydrogen fluoride. It has an electron-rich portion and it has an electron-poor portion. The partial positive is on the hydrogen side with a lower electron density. The partial negative is on the fluorine side where the lone pairs are for the higher electron density. That dipole moment or dipole shift is indicated by a cross arrow. One end is partial positive and one end is partial negative. And that effect is known as polarity. As it turns out, hydrogen fluoride has a polar bond and is also a polar molecule. That's because, again, there is a shift in the electron density towards the fluorine. Here's some tips that can help with identifying polarity of bonds. Tip number 1. Group 14 through 17 atoms form covalent bonds with each other. So, we have to first recognize whether it's a covalent bond. We'll know it's a covalent bond based upon its location on the periodic table. Group 14 through 17. You might note throughout many of my lectures, we talk a lot about using the periodic table. Tip number 2. Any two different atoms always forms a polar bond. So polar bonds are always formed by two different atoms, but not necessarily form polar molecules. We have to take it one step further to determine whether it's a polar molecule. In this lecture, you will learn how to determine a polar bond and a polar molecule. A molecule having a disproportionate electron density will be a polar molecule. Some molecules, by design, have a higher electron density and are therefore polar molecules. Lone pair electrons and an ion charge contribute to polarity. So if there's an ionic charge, then that will contribute to the polarity of the molecule. Tip number 4. Lone pairs are Lewis electrons that are not bonded. Since they're not bonded, they're free electrons that are available to attract a higher electron density. And that's what makes it polar in terms of its character. That's what makes the bonds polar, and that's what makes the molecules polar. So, again, polar bonds and polar molecules are those that have a higher electron density located at a particular region in the molecular structure of covalent bonds or covalent molecules. There are a couple of ways to determine polarity. One way that the polarity can be determined is by reviewing the electronegativity values. Atoms have electronegative values. Each atom, each element on the periodic table has an associated electronegative value. The trend on the periodic table is for the electronegativity to increase going from left to right and going from bottom to top. We can use some simple math to determine the difference between the electronegativity values of each of the atoms. That difference can then be used to decide whether or not an atom and the atom to which it is attached forms a ionic, covalent, or polar covalent bond. So in other words, the difference between two values of electronegativity will allow you to assign whether or not the atom is purely covalent, polar covalent, or ionic. The electronegativity difference is how we examine that. When the electronegativity difference between the two atoms is less than 0.4, it is considered pure covalent. When it is between 0.4 and 1.8, or actually you can round up to 2, it's perfectly acceptable. There are charts that report 2, and in fact in my own lectures you'll see both charts. So when it's between those values, it's polar covalent. When it's greater than 1.8 or greater than 2, then it's considered ionic. In general, most people just simply remember the rule of greater than 2. Okay, so greater than 2 means that it is ionic. Less than 0.4 or 0 means it's pure covalent. And between that range is polar covalent. And that's how we make our decisions mathematically as to whether a molecule is polar, or at least whether a bond is polar. And in some cases, it's one and the same. When it's a diatomic molecule, meaning two atoms, then polarity of the bond also is an indicator of polarity of the molecule, of the compound. In cases where you have more than two atoms, then we have to work through one other step to determine its polarity. But in simple diatomic molecules, again, those that have two atoms, the polarity of the bond is what indicates the polarity of the molecule. And so we show you a few examples here on this table for electronegativity. We have, for example, a CH bond has a difference of 0.4. its polarity shows a partial positive on the hydrogen and a partial negative on the carbon. In the case of sulfur and hydrogen, we also see similar partial negative, partial positive. It's an indication of its polarity. And so these are all polar molecules. And you see the other examples, and you see the big difference between hydrogen and oxygen, which is partial negative on oxygen, partial positive on hydrogen. And we know the OH is the chemistry of water. So that's pretty polar. And then we have the other examples. Carbon-carbon bond is nonpolar. CH compared to it again, and the SiC is partial positive, partial negative. And in this case, the silicon is a positive pole, and the carbon's a negative pole. Then we have SiO, and that's partial positive, partial negative. So that is how we can determine polarity based upon electronegativity values. We can also determine polarity by observation, which is used most often by freshman chemists, and certainly throughout just general chemistry more than the calculations are, frankly. So let's take a look at how we simply observe the atoms surrounding the central atom, or observe the atoms in the molecule, and make a decision as to whether or not it's polar or not. Okay? So, determining polar molecules by observation. For two atom diatomic molecules, if the molecule has a polar bond, then the molecule is polar. It is that straightforward. HBr is polar because it has polar bonds. Chlorine is nonpolar, as the bonds are nonpolar and the molecule is nonpolar, because the atoms are not different. So, as soon as you see two atoms that are different in a diatomic molecule, that is a molecule having only two atoms, straightforward, it is polar. And the direction of the dipole is toward the most electronegative atom. The most electronegative atom or element is the one that's located to the farthest right or near the top, furthest up to the top of the periodic table. Okay? Now, for three or more atom molecules, the molecule must at least have one polar bond to be considered. If there are no polar bonds in it, then there's no consideration to make. And the molecule must have an overall dipole moment. So we have to take it one step further to determine whether or not it has an overall dipole moment. For example, just because it has a polar bond does not mean it's a polar molecule, because there will be opportunities for that polarity to cancel itself out or cancel each other out. Lone pair electrons and charges have polarizing effects. So you tend to look for those species in compounds and atoms to help you make a decision. And we'll tell you some trends as we talk about these. Okay? So let's use these examples to walk you through how to simply look at it and observe it. In the case of carbon monoxide, we find that it has polar bonds. Why? It's CO. Straightforward. Two different atoms, polar bond. It is also a polar molecule because there is a dipole moment in the direction of the oxygen. Why? Oxygen is more electronegative than carbon, and therefore the electrons will shift their dipole in the direction of oxygen. However, in the case of carbon dioxide, CO2, it has polar bonds, but the molecule is not polar. Why? There's a shift in the dipole to the right and a shift to the left, or up and down. There is a shift in the complete opposite direction. When that is the case, then the dipole moment does not show up. It cancels out. And then there's aluminum chloride, or as it's generically referred to, aluminum trichloride. So there's aluminum chloride, which has polar bonds because the atoms are different. However, it is nonpolar because the dipole moment of the three chlorines attract the electrons. So the dipole moment shifts in the direction of the chlorines and they all three cancel out. So that makes aluminum chloride a nonpolar molecule even though it has polar bonds. And then we take trichloromethane, HCCl3. It has polar bonds. It has an HC polar bond and it has a CCl polar bond. It is also a polar molecule because the direction of the dipole is from carbon to chlorine, carbon to chlorine, carbon to chlorine, but then in the case of hydrogen, it's from hydrogen towards carbon. So there's an overall dipole in the direction past carbon out in the direction of the three chlorines. You can imagine this being similar to the hydrogen being the handle of an umbrella and the bottom part of the umbrella being the chlorine. So you have a dipole moving in that direction. So by observation, we can look at these molecules now and we can determine whether or not they are polar or nonpolar based upon our understanding about the direction of electronegativity on the periodic table. That direction is that electronegativity moves up and to the right as it increases. So within a column, within a group, the top of the column, the top of the group, has the highest electronegativity. In a row or a period, the atom or element to the far right has the highest electronegativity. Let's just look by observation at some more examples. We take a look at bromine and chlorine when it forms a bond. We note that the direction of the dipole is from bromine to chlorine, even though they're both halogens in group 17. Chlorine is above bromine on the periodic table, and therefore the polarity shifts in its direction. If we take boron trifluoride, in this particular case, we have an equal pull of the fluorines for the electrons. And in that case, it cancels out where boron trifluoride is nonpolar. We show you these electron density diagrams to support that claim. What about the dipole moment in some other species? Let's talk about what happens in methylene chloride. In the case of methylene chloride, we have a pull on the electrons toward the chlorines, and we have a pull away from the hydrogens toward the carbon to give us a resultant or overall dipole in the direction of the chlorines. So there are polar bonds and the molecule is polar. A particular group that you want to pay attention to is group 15 on the periodic table, because group 15 has a lone pair located on the top of the atom. That pair of electrons, that lone pair, has a tremendous pull on the direction of the dipole, on the direction of the electronegativity within the atom. And so, for example, in the case ammonia. For ammonia, there is an overall pull towards the nitrogen because of the lone pair. Because the hydrogens do not attract electrons. And that's a basic principle. Hydrogens do not attract the electrons. It's interesting to note, however, in the case of adding 3 fluorines to the nitrogen, there is an overall pull toward the fluorines instead of toward the lone pair. Keep in mind, because fluorine in its Lewis structure has 3 lone pairs on each fluorine atom and has an overall resulting dipole in that direction of about 0.24. Note the size difference between when you add a fluorine versus when you have hydrogens. Hydrogen, 1.46 in its dipole in the opposite direction of the similar compound when you add fluorine to it. So here we show you a table with some geometries and dipole moments just to give you an idea of what they look like. Note the very, very strong dipole on hydrogen fluoride and the very strong dipole on water. And the dipole on water is in the direction of the oxygen. So these are examples to give you an idea of what this dipole moment means and what it looks like. It's pretty interesting to note the difference between hydrogen fluoride and hydrogen iodide, HF versus HI. You see the trend with having I down near the bottom of the periodic table. It's less electronegative, far less electronegative in fact, than fluorine is at the top of the periodic table. So it's an interesting trend to note the 4 acids shown here. It shows the trend according to the periodic table. And that is something you want to make sure you remember. One of the ways that we're able to describe polarity and structures with regard to their polarity is by what's called the Vesper system. The Vesper system is the arrangement of electron pairs around a central atom in a molecule or ion, such that we get a representation of the electron pair repulsion, and that's why it's called the valence shell electron pair repulsion theory, or Vesper. Okay? So the Vesper theory allows us to examine the geometry of molecules and atoms, and as we examine them, we're able to understand more about why they have a dipole in a particular direction. So, how does it do it? Electron pairs repel each other in real molecules. That's what happens. Okay? So electrons, they repel. They're constantly pushing against each other. They also distribute themselves in positions around the central atom that are as far away from one another as possible. So the electrons attached to the central atom, the atoms attached to it that have electrons and have electron density, do their best to repel each other and push away. So you want to keep that in mind, and that's part of the Vesper structure. And that Vesper structure is what helps determine the quality of the dipole moment within the structure. And so we're going to look at these Vesper structures, and we're going to learn more about their structure and how it impacts the properties of different compounds and molecules. Okay? So within Vesper structures, we talk about the electron pair angle. The angle formed by any 2 electron pairs at the central atom is what we mean by an electron pair angle. So what's the angle formed once these atoms are added to the central atom and they repel each other, they push each other around until they find this energetically low position, that angle is called the electron pair angle. And so, what do we do then? We draw out these molecules, and we use a set of rules to draw them. I'd like to note, however, that some of you may find this to be intuitive and you can actually see it. Some students actually can see this. Some people can just visualize it. This helps us all to draw it and get going with trying to define what that Vesper structure is. Once you know how to draw them, you know how to draw them, and it becomes intuitive. You can see it. You can see how to space the atoms. You can see where the best position is so that they are equally spaced away from the central atom. For others, it might be more challenging. All right? So we're going to take you through some rules and some exercises to help you grasp the concept and be able to see these and visualize them so you can draw Vesper structures. Okay? So the first thing we really do is we draw a Lewis structure. So we're back to drawing Lewis structures. So you want to get good at drawing Lewis structures. Okay? The second thing is we count the regions of electron density around the central atom, both bonding and lone pair, and that is so important. Oftentimes, students overlook the lone pair. So essentially, you want to look at the central atom and decide what fixtures are around that central atom. Whether it's a lone pair, whether it's an atom, whatever it is, you want to count it. So basically count the items attached or located around the central atom, including the lone pair. Then you want to determine the electron pair and molecule. Okay? So you want to determine what it looks like. You want to push the electrons around until you can see the geometry of how it fits around that central atom. Fortunately for us, much of this has already been done. So we can take the summaries and use them in our discussions about the geometry of atoms and molecules. So let me back up. Vesper structures are the drawings, the geometrical drawings that chemists use to determine its spatial orientation. How does this atom fit in real space? Where does it sit and where do the atoms point? And how do they find a way to repel each other, yet hold itself together and find a low energy position where all the atoms are reasonably comfortable, including the lone pairs. Although it's not an atom, it holds a space in the geometry. Okay? So there's a space for the electrons in the geometrical shape. So you want to keep them in mind. So let's walk through these then. Here we're going to teach you by showing you examples. Linear, not too hard to figure out, right? The central atom, here's the blue ball, and on both sides we have two. The best position is north and south or east and west, up, down, or left and right. There are only two fixtures or two groups associated with this central atom, and therefore it's 180 degrees. Just know your geometry, which you already know. Just look at your geometry. It's 180 degrees from one side to the other. So it's linear. That's what forms with group 2 as the central atom. Linear geometry results when group 2 atoms are in the center of a compound. Now, when the central atom has 3 groups attached to it, that forms a trigonal planar geometry. That is the case for group 13 central atoms. Keep in mind, we number our periodic table 1 through 18. You should also be aware of the nomenclature that uses the A and B grouping. This would be 3A. So, for group 13, central atom, such as boron and aluminum, we get 180 degrees between the molecules attached to the central atom. Group 14, forms tetrahedral. Tetrahedral has bond angles of 109.5 degrees. That's for each of its tetrahedral angles. So it has 4 different groups attached, and a tetrahedral has a 3D look. So oftentimes wedge and dashed lines and straight lines are used to draw out a tetrahedral shape. That brings us to group 15, and we have the example of ammonia. Ammonia has 4 atoms associated with it. Of those 4 atoms, we have 3 bond pairs. And then we have 1 lone pair, which means we have 4 different groups coming from that central atom that we have to account for. That gives us a trigonal pyramidal form, where the top of the pyramid holds the lone pair. That is the geometry for group 15. For group 16, we have water as our example. 3 atoms, 2 bond pairs, and 2 lone pairs. Therefore, we have a bent geometry with the 2 lone pair electrons taking up positions as well. This table, table 13.2 in this lecture, has structures for other geometries and how we view that geometry. We will not spend time to go through this table in detail. However, it is expected that you'll be able to look at this table and understand the geometries. We see on this table the tetrahedral, we see the linear, and we see the trigonal. We also see the bent. We see the trigonal pyramidal. These are the geometries that we expect you to be familiar with in CHEM 111. Now, we said to you that the geometry affects the dipole, or the dipole is influenced by the geometry. And so we show you in this slide how the linear geometry of carbon dioxide is influenced by its geometry, and not only its geometry, but the electronegativity of the atoms. In this case, because it's 180 degrees, we find that the equal pull of the oxygens away from the central atom cancels the dipoles in this linear structure. However, in the case of the bent water molecule, the pull of the electrons toward the oxygen and then out in the direction of the 2 lone pair gives an overall dipole, as shown in this slide, that goes in the direction of oxygen and the lone pair. If we take a look at a tetrahedral, we have different dipole moment directions depending on the atoms attached to the central atom. And we show you that in, for example, carbon tetrachloride. In this case, it has 4 equal pull of chlorine atoms, and that cancels the dipole. So there's no dipole. In the case of trichloromethane, we have an overall pull in the direction of the chlorines. Likewise, in methylene chloride, we have an overall pull, or a net dipole, in the directions of the chlorides. In the case of chloromethane, we have another net dipole in the direction of the chlorine. But in the case of methane itself, CH4, there is no net dipole, which means that carbon tetrachloride on the far left, CCl4, and methane on the far right, CCH4, are non-polar molecules. even though they have polar bonds. In the case of the other three tetrahedral geometry compounds with carbon, group 14 at the center, these have a net dipole, and therefore they are polar molecules, and yes, they have polar bonds as well. So this is why understanding the geometry, the Vesper structures, is also very important. It helps us to determine or helps us to observe whether or not there is the potential for a dipole moment, even if we don't have the calculated values. And those calculated values coming from the electronegativity. So let's practice an example here. We're going to determine the polarity of OF2. Okay? Now, what we notice is that we have F and we have O. We can look up the electronegativity values for fluorine and oxygen, and what we find is that the electronegativity value or difference would be 0.5. So the difference is 0.5, with fluorine having the highest value. So since we have a 0.5, that means the bonds are polar covalent. So these are covalent bonds and they're polar covalent. However, you suspected that they were covalent because the atoms that are attached are located in group 16 and group 17. So, therefore, we have polar covalent bond. Is the molecule overall polar? To determine that, we draw the Lewis structure. We show you the dot structure to the far left on this slide. And we note that there are 8 electrons around oxygen and 8 around both of the fluorines, which makes for a really good Lewis structure because it fulfills the rule of 8 octet. When we look at its geometry based upon its Vesper structure, we find that it is a bent molecule and it has 2 lone pairs occupying 2 of the groups, 2 of the spaces around the central atom, and 2 fluorines occupying the other 2. And we note that the pull of electrons are in the direction of fluorine. Therefore, yes, it is a polar molecule because there's an overall pull of the electrons in the direction of the fluorines. So, OF2 has polar bonds and it is a polar molecule. One of the results of a discussion on polarity is that we discover that electrons have mobility, and that mobility for covalent bonds is through the bonds. That movement is through the bonds in the direction of the most electronegative element. Electrons also can move as pairs by rotating throughout some molecules. Some molecules and some molecular geometry, it's such that pairs of electrons can rotate from location to location. And it can do that as long as it can resonate with the other atoms. That flipping or movement of electron pairs is called resonance. So let's talk about resonance forms and what resonance means. In certain cases, a single Lewis structure does not adequately predict the properties of a molecule or ion. In other words, when we draw a Lewis structure, we fix the electrons in a position or at a location. But we now know that these electrons have mobility. We know that they gravitate toward electronegative elements and atoms. And we're now going to learn that they also can flip electrons, flip lone pairs, flip pairs of electrons throughout the atoms. Because of that feature, the Lewis structure does not adequately describe the molecule or the compound or the groups of atoms. For these compounds, two or more Lewis structures can be drawn. So we just draw different structures. These individual Lewis structures are called resonance forms. So resonance forms are Lewis structures with mobile electron pairs. In other words, a single resonance form does not exist. That brings us to a definition of resonance. If two or more Lewis structures with the same arrangement as atoms can be drawn for a molecule or ion, then the actual distribution of electrons is an average of that shown by the various structures. In other words, the true structure or the true representation of the structure is composed of all the possible drawings of that structure, which we call resonance structures. In other words, the true structure isn't the one, it's all of them. So here we show you what that looks like. When you draw resonance structures, take care not to go against the rules of chemistry or the rules of science. So not every compound has a reasonable resonance structure. When we draw resonance structures, we do our best to hold them to the rule of 8 as often as we can. Okay? So, in the case of SO2, we show one resonance structure on the left. If we look around each of the atoms, we find the rule of 8 for all the atoms. That is, for the oxygen on the left structure, for the sulfur on the left structure, and for the other oxygen. So, what do? We can take the electrons now from the right-handed oxygen and shift them in the direction of the sulfur. And if we do that, we then flip the left-sided double bond out, and we get a resonance structure. So, the way you move these around is by flipping one set in and another flips out. So that's kind of how the rule works. It's like a swinging door. One door opens, the other must close. If one closes, the other opens. If we move a set of electrons off of one atom, that means another set of electrons must move off another atom, off the adjacent atom. So, when we do resonance structures, in general, you will move at least 2 pairs. In general, for a resonance structure, for freshman chemistry, you will move at least 2 pairs. If you don't move 2 pairs, then you might not have drawn the proper resonance structure. So you want to think and ask yourself, did I move 2 pairs of electrons, a total of 4? Okay? So, take a look at the next set of NO3. Just simply stare at them and you will see the difference from the first structure to the middle one. We flip the bottom electrons, lone pairs, off the bottom oxygen. We flipped it up, and then we flipped the double bond on the right oxygen out, and we got the middle structure. Then we took the middle structure, left top oxygen, flipped 2 electrons in, and we flipped 2 electrons out on the bottom to get the far right structure. So it's basically a movement of electrons. You do well to watch a video on this so you can clearly see the movement of electrons. Okay? But a resonance structure allows you to shift pairs of electrons. And for most of the ones you would see in freshman chemistry, it involves at least 4 electron movement. 2 in, 2 out. 2 in, 2 out. 1 bond in, 1 lone pair out. You get it? 4 electrons. Never do a resonance structure with 1 dot. Okay? Resonance structures will involve a line or 2 dots or lone pairs. Keep that in mind. So, when it comes to resonance forms, the actual structure of a molecule is an average of the resonant forms known as a resonance hybrid. These bonds are intermediate in length between a single and a double bond. And in fact, that's how people in laboratories know that there's a resonance form. In research, they know this because when they measure the bond lengths, they can see that it's shorter than what would be a normal single bond or a normal expectation for that type of bond. And that suggests to them that there's some type of movement in the electrons. And that movement is called resonance. Here we show you some other resonance forms. Ozone, which is a pretty popular one. We have movement of the electrons on the far right. Oxygen in the first structure for ozone, O3. It pops 2 electrons toward the middle, and then it kicks 2 electrons out to the left. And so you get the resonance structure. It doesn't matter, by the way, which one you start with. Since they're all hybrids, there is no superior resonance structure, although that's not completely true, but you will learn that as you continue your chemistry career, that there are some preferred resonance structures. But for the most part, for the ones that you'll see in Gen Chem, there is no real major difference for you to consider. In the case of NO2, we do the same thing. For the oxygen on the far left, it pops 2 in and it kicks 2 out to get the structure. Then we show you HPO4. Same type of thing. We can go around in a circle, 2 in, 2 out, 2 in, 2 out to do resonance structures. How about one other example? And if you note, the electron count never changes. The number of valence electrons used in all the structures are the same. You can't throw away electrons. You can't add electrons. You must maintain the electron count. That's one way you'll know you got it right. So if you want to check yourself, recount your total electrons. Okay? In the case here, you have structure A can become B by flipping in the negative charge on the left nitrogen, and then it pops the double bond to the oxygen out to form one more lone pair, and then the structure can go over and over until it matches C for another resonance form. Okay? All right? And in the case of these ionic compounds, the charge will still work itself out to be the same charge you start with. So you cannot change the charge value, you cannot change the electron count, and you do not change the connectivity of the atoms. Once the connectivity of the atom has been established, the base Lewis structure has been established, you don't change the connection of the atoms. Resonance structures only move electrons. That's all that moves. Only the electrons, not the atoms. Well, let's talk further then about formal charges and Lewis structures. For neutral molecules, a Lewis structure in which there are no formal charges is preferred to one in which formal charges are present. In other words, you want to draw a Lewis structure where there are no charges, formal charges, on the atoms. So you want to balance the electron count across the atoms in the structure, in the molecule, until all the atoms have a neutral charge. And we're going to show you how to calculate that charge and how to observe the molecule and determine that charge, simply by observation, in what we call a quick count. Lewis structures with large formal charges are less plausible than those with small formal charges. So if you have to have a formal charge, make sure it's 1 or 2. Okay? If you have a formal charge of greater than 2, you might have missed an opportunity to draw a better Lewis structure. Point number 3. Among Lewis structures having similar distributions of formal charges, the most plausible structure is the one in which negative formal charges are placed on the more electronegative atoms. So in other words, the negative charge should be on the atom that's furthest to the right in the row along the period, and should be furthest to the top in a group, because that is the trend for electronegativity. So be sure you don't put the negative charge on the most positive atom. That means you've not drawn the best Lewis structure. This is why knowing the trends in electronegativity are so important. So let's try doing this. Here we show you an example of doing formaldehyde. First thing we've done is draw out just a simple stick model. You draw the atoms out, and then you start to inspect what the possibilities are between the choices. So we draw one. So we show you here the 2 choices that we're looking at. Okay, ready? An atom's formal charge is the difference between the number of valence electrons in an isolated atom and the number of electrons associated to that atom in a Lewis structure. So this whole process starts by drawing a skeleton and determining which one is the best skeleton based upon the formal charge. So the formal charge on an atom in a Lewis structure equals the total valence electrons in the free atom minus the total number of electrons of non-bonding electrons minus 1/2 the total number of bonding electrons. So those are the shared electrons. So we're going to do it using the calculations, and then we're going to show you how to do it by what I call quick count, quick check. Okay? The sum of the total formal charge of the atoms in the molecule or ion must equal the charge on the molecule or ion. If it's neutral, it must come out to 0. If it's something other than 0, it must equal that value. Now, talking through this sounds more complicated than it is. This is not deep level math. This is simply look at the values, subtract, and get a value. Do not make it more complicated than that. So that's how we're going to show you to walk through it, okay? We're going to walk through the example and just calculate it, and you'll see how to do it that way. And then we're going to show you a method of quick check to do it, all right? So, for example, if I don't ask you how you got it, I'm okay with either method, okay? In some of the problem sets, it may ask you to show a particular method, and this is the method you'll show, okay? All right, so let's just walk through it. We have the skeletons drawn. We have 2 possibilities, the A group and the B group. And let's just see how it all works out. In B, the C atom has a total of 4 electrons from the breaking of 2 single bonds and a double bond. So simply just plug it into the formula. Do not make it more complicated than that. Don't overread this. So the formal charge is 4 minus 4 equals 0. It is that straightforward. This, quite frankly, is where the quick count method comes from. The oxygen atom has a total of 6 electrons, 2 lone pairs and 2 electrons from the breaking of the bonds. In other words, you're splitting the bond in half when they're shared. Okay? So they're basically taking their share of the bonds. So you split them in half and you simply count. Do not do any deep arithmetic or deep math here. Just count. Therefore, the formal charge on the atom is 6 minus 6 equals 0. Although both structures satisfy the octet rule, B is the most likely structure because it carries no formal charge. In the case of A, we have a formal charge. So if, for example, on a standardized ACS test, If you saw these two structures, take the one with no formal charge. You get it? If you count through this, use a simple equation, it will make sense to you. Do not complicate it, simply count it. So, let's do it here on this slide. Formal charge calculation. Ready? Here we go. We have carbon, 4 electrons. Oxygen, 6 electrons. 2 hydrogens, 2 times 1 electron for a total electron count of 12. We have 2 single bonds. So 2 times 2 is 4. 1 double bond means 4, double the number of electrons. 2 lone pairs, 2 times 2, 4. Total equals 12. Okay? If we look at the formal charge on carbon, we have 4 minus 2 minus 1/2 times 6 will be a minus 1. The formal charge on oxygen would equal 6 minus 2 minus 1/2 times 6 equals plus 1. Plus 1 minus 1 cancels each other out, and that makes it neutral. Okay? But this structure is less preferred because we have formal charges on them. But we wanted to use this to teach you how to calculate it. Take time, read through the slide again, and I'm sure you'll pick it up. It's straightforward. It's not really that deep. Now, we'll show you what I call the quick count. And here's how the quick count goes. Ready? Carbon should have 4 by its Lewis dot structure, by its valence electrons, by its position on the periodic table. But carbon has 5, so subtract. The number it has, you always subtract them. Therefore, it would have a minus 1. Oxygen should have 6. It has 5, which you subtract, so it's a plus 1. So that's the quick count method. So you take the number it should have minus the one that it has. That gives your electron charge. Minus 1 and plus 1. That's how we do it by simple quick count. Let's take another example. Using this other structure of formaldehyde, we have same electron count, no change in electron count. However, the distribution of the electrons, the connectivity does influence the character of the final compound. That is, its electronic characteristics. Okay? So in this case, we have a charge of 4 minus 0 minus 1/2 gives us 0. Oxygen, 6 minus 4 minus 1/2 times 4 equals 0. So in this case, we have a 0 charge on carbon, 0 charge on oxygen. This is the preferred structure. Again, read through it slowly, and I'm sure you will pick this up. Quick count method is also shown where we include hydrogen just so you see the process works. Hydrogen should have 1 minus the number it has, which is 1. So we're okay there. 0. Carbon should have 4. We look just around carbon. It has 4. 0. Oxygen should have 6. Only around oxygen. We split them up, and it has 6. Therefore, 0. So of the structures for formaldehyde, the preferred structure would be the one that we show you here, where both hydrogens are bonded to the central atom of carbon and then oxygen. You intuitively knew that because you knew that carbon had the opportunity, because of its valence structure, to attract 4 different electrons, and this structure just intuitively made sense to you. But we've shown you how to walk through the calculations and acquire the charges. Let's look at another example. We have the carbonate anion, which is minus 2 here. The way we look at it is by visualizing where we break the bonds. And what we observe is that carbon should have 4. And it does have 4. So it would have a charge of 0. And then we have to go through now and assess the charges on the oxygens. But the oxygen we look at is the oxygen that is double bonded to determine what its formal charge is. And when we look at that oxygen alone, it has a formal charge of 0 because when we break it, we see that we have 2, 4, 6 electrons around the top oxygen. But then we have 2 more oxygens that we have to consider. When we consider those 2 more oxygens, we discover that we have 6, which is what oxygen should have, minus the 6, minus 1, leaves it with a minus 1 per each of those oxygen atoms. Straightforward math. Don't complicate it any more than that. And that's why we have a minus 2 on the carbonate anion. We can get the same answer by the quick count method we show you here, where carbon should have 4, and it has 4 for a 0. We do the 2 oxygens that are on both sides of the carbon. We do those 2 oxygens. Both of those should have 6, but they both have 7 for a minus 1 each. And then we do the oxygen on top, and it should have 6, and it does have 6 for 0. So both methods, the math, simple math, finger and toes math, straightforward math, gives us the answer we find as a minus 2. And also our quick count method gives us the answer at a minus 2 as well. So the sum of the charge on carbonate anion, which is a polyatomic anion, is minus 2. And that finishes Lecture 2 of Chapter 7, Chem 111. Lecture 2 of Chapter 7.